Suji gauge series. Okay, so this is one thing. And how it's connected with the geometry of the three manifolds. Well, it's not necessary geometry. We can talk about quantum corrections, etc. So I call this 3D SL to R chern-simons theory. Or if you like a more geometrical language, which corresponds to a semi-classical limit of this theory, the three manifolds, the geometry of three manifolds, or geometry of three manifolds. But before talking about this, I'd like to give you a little bit of overview of why I'm interested in this. And well, now is the time when LHC is discovering a lot of, well, haven't discovered Higgs yet, but a lot of, well, we have heard a lot about exciting experiments at LHC. And now, as a formal theorist, the question is what we are going to do now. And of course, depending on perspective, there are different things to do. But I think one thing we can think about it is the problem, very old problem about supersymmetric gauge series. And of course, supersymmetric gauge series has a lot of history of more than 35 years, and it was invented even before I was born. But what's surprising about supersymmetric gauge theory is that there are some interesting new developments still in this field, still after 30 years, maybe 35 years after the discovery. And one interesting result is about the exact computation of the supersymmetric series based on compact manifolds. And what I mean by this, I start from 4D n equal 4 series, or sorry, not 4D equal 4, 4D series. Well, there are various different quantities you can compute, depending on the number of supersymmetries, depending on dimensions, etc. But one quantity which you can compute is the 4D partition function it's like the 4D partition for n equal 2 series. For example, on S4. Or if you want to study 4D series, you can prepare any, well, not any, sorry, 4 manifold, and then another good candidate is S1 times S3. And this is known as a super conformal index. And since it's, well, what's interesting about this case is that if you have S1, then you can turn on a lot of chemical potentials. And so there are chemical potentials. So it's a function, it's not just a number. And you can compute it, since it's an index, so it's a super conformal index. And you can compute it by going to the free field limit, etc. And, well, there are another quantities, which is the 3D n equal 2 series. And you put it on S3 and compute the partition function. Again, you have a certain number. Or more generally, this 3D n equal 2 series has a set of parameters, like a mass parameters, Fi parameters. So this is going to be a function of these parameters. Or you have 3D n equal 2 series on S1 times S2. And again, you put down some chemical potentials. So there's going to be, and the interesting thing about these quantities is that, of course, it's easy to formally define as a path integral. But what's interesting about these is that we can compute these things exactly. Exactly meaning these are first leading as a path integral. But now that there is a localization computations procedure, which shows that these reduce to the computations in the matrix integral. So they're going to become the finite dimensional integral, so we can compute it. And then these have powerful techniques to study these series. For example, there are a lot of dualities. Say, for example, there are 3D mirror symmetries, which are discovered in the 90s. And we can compute these partition function, these super conformal indices, or well, this is also index. And a partition function, and try to see whether they really match. And if they match, it's quite often quite miraculous identities of spatial functions, and then they're going to provide checks of this dualities between in 4D and 3D series. And these are the quantities. But sometimes we can make a connection between these quantities. For example, if you start from 4D n equal, say, 1 series.
What is the matter content?
For the most cases, matter content is pretty general. For example, let's say, so for example, in this case, we have just a chern-simons, gauge coupling chern-simons term, matter term, etc. And as long as it's 3D n equal 2. So it's rather general. I mean, the same is true for all these cases.
Why do you say for n equals 1, you can only do S1 cross S3 as opposed to S4?
I don't have a simple explanation for that, but I'm glad to have some simple intuitive explanation why the computation doesn't work for 4D n equal 1. But at least, what we do in these cases is to start on the Lagrangian. First of all, the Lagrangian in the flat space, and we try to put the theory on the curved manifold. So the Lagrangian itself is corrected. Supersymmetric transformation is corrected. If you denote the radius of this S4, there is going to be one of R corrections to everything. And you'd like to first find the supersymmetric transformation, Lagrangian, etc., such that everything, for example, 3D transformation closes off. And then once you find the supersymmetric transformation, then you can choose the appropriate Q exact terms, add Q exact term to the Lagrangian. And then you have to choose that carefully. And after that, you can do the standard localization computations. And this first integral reduces the sum over the solid points, which in this case is the integral. So we're going to have an integral arising from that. And the good thing about this, for example, about these manifolds are that they are conformal flat. So I mean, in order to write a supersymmetric transformation, we need Killing spinors. But these are conformal flat, so we have a conformal Killing spinors. And using that, we can write down the supersymmetric transformation. So all that requires a careful analysis. And many of the analysis in these cases are similar, but details are slightly different depending on various dimensions and various manifolds you can consider. And then, well, of course, there are some, but these, so depending on series, we can construct such a lot of quantities, compute them. And there are some interesting relations between them. For example, if you start. Oh, let's see. Well, actually, that's also a good question because, for example, this quantity is usually called the supercomponent index, and it's defined in order to extract some quantities which are invariant at the marginal deformations of the 4D, say, n equal 1 supercomponent Q series. But actually, these quantities can be computed for series which are not conformal in the UV and close to non-trivial fixed point in the IR. Because as I said, the procedure, well, for example, in this case, there are two different ways of computing that. The first is go to the free field limit, saying that this is the index. So it's invariant under continuous deformation. We can go to the free field limit, and then everything becomes a little bit trivial, not completely trivial, but trivial computations. That's one way. But another way is to do this localization as the thing. And if you look at the localization computation, you really see that you don't really necessarily need the supercomponent invariance at the UV, for example. So you can compute that for. And that's how people try to check this Zybach duality for 4D n equal 1 series. People, I mean, these series are different and it's not conformal on the UV, but you can compute these quantities on the UV and then try to say that. And then what's interesting about these quantities is that, well, in general, says these gauge series have gauge coupling in the Lagrangian. But these quantities are don't depend. For example, these quantities don't depend on
the one on the left does.
Yeah, that's right. So actually, I have to. So these quantities, for example, are, as I said, the index, so they don't depend on that. So, and
Can you remind us why it is an index? Is it because of this S1 factor?
Oh well, actually, because I defined the index, this partition function as literally as an index. So maybe I should simply, if you like, I should call this index index of I4. I really define the index as a.
It's just because of this S1 factor, right?
Yes, that's right. So because of the S1 factor, we can turn non-trivial twist along S1, and of course, I was talking about this Killing spinors, etc. So I have to make sure that these boundary conditions twist are consistent with these spinors. And then there are some operators. Well, for example, there are energies, free energy, anyway. Spins, etc. R charges, maybe. No. But anyway, the details don't matter too much. But anyway, if you like, I can write on the more formula. For example, well, the formulas are not important. It's just that there are spins, energy, spins, R charges. There's going to be, for example, chemical potential for the n equal 2 superconformal index. And what's interesting about these quantities is that there is another interesting thing about these quantities. Sometimes there is a connection between these two. So if you start from for the n equal 1 series, and we can compactify S1 times S3. And if you start, even if you start from superconformal field series, the resulting series is not conformal because there is an explicit scale involved in this S1, but you can go to IR, and there's going to be some non-trivial 3D if you start for the n equal 1 3D, n equal 2 series in the infrared. And then there's a systematic deduction procedure starting from the 4D n equal 1 series index and go to the 3D n equal 2 partition function of the same series dimension reduced on S1. And then there is well, it's roughly speaking just a Kautz-Klein deduction where you neglect all the modes of S1. But sometimes you have some interesting chemical potentials which you can turn on, which corresponds to some deformation, or one parameter deformation, one parameter which I will speak here of this S3. Or you can actually go to this direction by dividing S3 by ZP, where ZP acts on the S1 of the fourth vibration of this S3, and take the limit where P goes to infinity. So this ZP acts on S1 of the fourth vibration. Maybe I should so people can see. Anyway, but anyway, details are not too important for my talk because, as I said, I'm going to talk about these theories. But the point is that there are a lot of interesting quantities which you can compute, and there are various interesting relations between them. And this is about the world of supersymmetric series. But there's another thing which is fascinating about the supersymmetric gauge series these days, and which is that there is a relation between supersymmetric and non-supersymmetric series. Well, relation is a little bit ambiguous word, so I like to make it a little bit clear. And it is come from the dimensional reduction, believed to come from the dimensional reduction of the mysterious series, 6-dimensional 2, 0 series. And a good example for this is that first of all, so let's see. So let's start from 60 2, 0 series. It's a series which is believed to exist coming from the argument of string theory, and then there's a story about reducing this on the Riemann surface, and you have 4-dimensional. There's a story about Gaiotto and his collaborators that we have a 4D n equal 2 SCFTs. Well, the details of this, some parts I'm going to explain, and other parts I'm not going to explain, will not be needed for this part. So please don't worry about this. But I think basically the idea is that if you start from 60 series and compactify the Riemann surface, you have for the family of 4D n equal 2 SCFTs. And the prototypical example for this is that if you have just a torus, T2, and then you have 4D n equal 4 series, which is the simplest series of this class, and then there is a complex structure moduli of the torus, and that's going to be identified as the complex gauge coupling of this 4D n equal 4 series. And there is a mapping class group which changes the torus, fundamental region of the torus, and that's going to be the S duality of 4D n equal 4 series. And then these are the generalization of that story to arbitrary Riemann surface with punctures and genuses. Anyway, and what's interesting about this is that there is a description of some of the quantities here in terms of 2D theory. 2D theory on the Riemann surface. This Riemann surface is the same Riemann surface as here. And well, I know 2D theory, so what kind of theory do you have? And actually that depends on what kind of quantities we are going to consider here on this side. And one quantity which you can consider is as a load, the partition function of this 4D theory on S4. 4D theory on S4. And then the corresponding 2D theory is this is going to be the Liouville theory. And the statement, the relation in this case is that the partition function of this theory on S4 is the same as the correlation function of the Liouville theory on this Riemann surface. And that's the story of the now called AGT story of Gaiotto Tachikawa relation. Or you can start with other different quantities which allow index I. So I can start with index from S3 times S1. And then here we have 2D Q-deformed diamonds. Q-deformed diamonds. Although, actually, and this is a story by Gatte, Stony Brook group, Gatte, Rastelli, Razamat, Yan. And well, even for this case, not everything has been understood because there are a lot of chemical potentials here, and there are no corresponding parameters here so far, so people are trying to identify the parameters on this side. But anyway, so depending on various quantities, you can consider theory here. And it's a lot of mysterious why we have such 2D series, specific 2D series, U-view, etc. And it should be coming from this dimensional reduction from this 60 2,0 series. So, and it's an extremely interesting problem to see what kind of implications these relations are going to have on the 60 2,0 series. But not going to be the problem I'm going to discuss today. But the problem I'm going to discuss today is that, well, instead of starting with these, dividing 6 dimensions into 4 and 2, and we can start from 3D n equal 2 series, 3D n equal 2 SGFT. Well, it's not, well, it's going to be non-conformal in the UV, so but it's going to flow to a non-conformal fixed point. So depending on the preference, we can call it SGFT. And so it's going to be 3D series, supersymmetric series. And these are going to be related to 3D SR and R. But for the purpose of my talk, let's specialize to a particular gauge group. So let's take this to be A1 gauge theory. I mean, when you dimension reduce, we're going to have SU2 gauge theory. And then that corresponds to SU2R, chern-simons theory. And, well, I forgot to say that this is work in collaboration with Yuichi Terashima, who is a mathematician, and my paper has appeared. And actually, these papers it's stimulated by these 2 papers. The first is by Nadaf and Davide and Jama. Let's see, got it. It was March or April, I forgot. Anyway, and then there's the paper by Hosamichi, Lee, and Park. So these first 3 authors proposed a general idea, and then these 3 people gave a very explicit computation for that. So this is some. Sorry? Let's see. So that's what I'm going to explain. Right? But simply put, it's a relation. Well, the partition function of this 3D series, these people conjecture is the same as the duality kernels which appear in this Liouville theory here. And then these people did the explicit computation of the 3D partition function, and they verified that they are the same. But I need to explain, before coming to that. So the story is, what I want to do is to start from the 3-man. Well, this is going to be a certain theory. Well, I said that it's a 3D chern-simons theory, and I hope to explain that, why it's the case. But I need to define it on a certain 3 manifold. So let me call it M, where M is a 3-dimensional manifold. And what we'd like to do is to give a corresponding 3D n equal 2 theory, Tm. But this is now becoming probably the standard notation these days, corresponding to these 3 manifolds.
M is closed and compact?
Not necessarily closed, actually. It can be open. And
so it has a boundary?
Yeah, it has a boundary.
But it is.
In general.
It's not an infinite, right?
It's not infinite. So for example, the prototypical examples we talk about is the Riemann surface times an interval, for example. Oh. So it has a boundary at the endpoint of the interval, for example. Or we can consider more complicated knot complement, for example, or the manifold obtained by gluing this tetrahedron, etc. But anyway, well, of course, it's easy to say that there should be some 3D series and a 3D supersymmetric series, and then there's some quantities should be the same. But of course, the difficult part is to identify precisely pitch quantity on this side is the same as precise pitch quantity on that side. And also precisely pitch theory corresponds to pitch 3 manifold, and that's the non-trivial part. And first of all, I'm going to say that it's going to be the 3D partition function. So I said that there's a 3D partition function here. It's a 3D partition function on S3. So this is a 3D n equal 2 series, and let's compute the partition function S3. And I want to construct the series Tm such that it's the same as SR to R chern-simons partition function on M. So this is going to be the statement. And if you like, you can try to consider different quantities, like a superconformal index in this side, and then the question still remains what are going to be the corresponding quantities on this side. But let me focus on this particular example.
Are there any restrictions on the type of 6 manifolds which you consider theory on?
Well, actually, there can be. I mean, some of the things I'm going to say can be a little bit tricky in 6D. For example, I said that these can have boundaries, like a Riemann surface times interval. But from purely 6D viewpoint, I think it's fair to say that what the meaning of the boundary is not too clear. I mean, if you have M2, for example, you can end on M5, but maybe M5 has gone off to infinity.
In the 40 case, if you magnified on Riemann factors or some
Oh, actually, this side is always S4, and this side you're going to have a completely general punctual Riemann size. And similarly, we have the geometry here is going to be fixed. It's just S3, but we are going to have manifolds. And then, well, I hope to explain what are these going to be. But these.
The boundaries of M in some sense.
Sorry?
You read this from sense analogous to the factors on the Riemann surface.
Yeah, so boundaries are the counterpart of that. So, and actually, that's actually a very good point. So I'm going to try to advocate. I'm going to advocate that point actually. So well, of course, as I was repeating, the question is how to identify the Tm, and we need to. I mean, if you start from nowhere, then we are going to. I have no idea what to proceed. So the good strategy is to learn from this 4D n equal 2 series, and what we did for that. And in that case, recall the 4D n equal for this Gaiotto story, and there you have a certain Riemann surface. Say for example, let's see, you start with the Riemann surface, and say for force puncture sphere, for example, here. Okay, so this is a Riemann surface with 4 punctures, so this is double coupled. And then what we can do is to consider the punch decomposition of this, so-called. In other words, this just varies the complex structure of this force punctured sphere, and we have a certain cylindrical region inside. And then we can decompose this into 3 parts. The first, this part and that part. So this part is a 3-punctured sphere. It's called a trinium. And this part is a cylinder. And there's another trinium. And the basic idea of the video is that whenever you have the cylinder, we have SU2. Well, sorry, again, I'm talking about SU2 gauge case. Gauge group is SU2. SU2 gauge factors. And it's going to be, well, in the case of SU2, it's a trifundamental. And then there are these S1s here. And each of these S1 correspond to flavor SU2 gauge symmetries. And when we say that when we group these 2 triniums together, there are 2 SU2s. If you don't have this cylinder, there are 2 S1s here and there. So they are SU2 times SU2 global symmetries. And we are going to gauge the diagonal part of that. That's the geometrical meaning for the concatenating the cylinders to triniums. Okay, so now the question is what happens for the 3-manifold case. And we are going to try to imitate this. Although, actually, there are going to be crucial differences. So this is not a complete analogy, and then there are a lot of differences I warn you. But there are certain similar stories you can consider. So first of all, in this case, the one crucial ingredient is a cylinder. Well, in this case, the cylinder is a 2-manifold, and it's just a circle times an interval. But now, if you want to study the three manifolds, so why not generalize this to higher dimensions? So we start from the Riemann surface and times an interval. And for the moment, let's not talk about punctures here. And then we have the Riemann surface. And then there is just the interval, 0, 0, 1. And then this obviously has boundaries. And the question is, what's the thing corresponding to that? And so let me call this sigma, and the whole thing M is sigma times interval. And as I said, I'm going to use the old 4D, 2D correspondence. So I'm going to translate each of these into the supersymmetric gauge theory language. And of course, if you have sigma, the rule of thumb in this ADT story is that it should correspond to 4D n equal 2 series, 4D2 n equal SCFT. And since there are two boundaries, we have 4D n equal 2 SCFT. Okay, and there should be something in the middle corresponding to the three manifold. And the proposal is that it should be a certain domain wall which divides this. So you can start from 4D series on R3, 1, and put a non-trivial domain wall R2, 1 inside it, which divides the space into the right-hand side and the left-hand side. And then if on the duality, well, let's see. So this is the domain wall. And well, the question, of course, is what kind of domain wall we consider. And well, I'm going to consider something called the duality domain wall. So this 4D n equal 2 SCFT has a complexified gauge coupling, 4 pi I divided by G squared. Complexified gauge coupling, and this is going to be the complex structure of the Riemann surface. So complex gauge coupling is translated in complex structure. That's the Gautos dictionary, which I'm introducing now. And there's another ingredient is that there is an element of S duality group, which is identified with the element of the mapping class group. Well, mapping class group is a diffeomorphism of the Riemann surface, which is not continuously connected to identity. So it's a discrete gauge, well, discrete transformation on the Riemann surface. Which in the case of, say, if this is just a torus, again, it's just for this is just PSL2Z symmetry for the n equal 4 theory, and that's mapping class group for the torus. So it's a generalization of that. And now the crucial ingredient is this, this element of mapping class group. And this element of the mapping class group can play a role in this story, because when I start from here and I'm going to, so in order to consider some 3D theory here, we need to put some appropriate boundary conditions here. And if you want to use the similar story to this, we need a Ponce decomposition of the Riemann surface here. But the Ponce decomposition here and there can be different. So that's going to be represented by an action of mapping class group. Or anyway, there can be something non-trivial in the middle, and that's what I'm like as an element of mapping class group. In other words, if you want to, for example, you can try to close this up to make the interval into a circle. So, and then it's going to be the Riemann surface times a circle, but we can add a non-trivial twist along the circle to make the three manifold more non-trivial. And that's going to be here. And correspondingly, there is something here which is specified in an element of the S duality group, and that's the duality domain wall. And the meaning of the duality domain wall is the force. So I start in the value of the complexity coupling tau and phi of tau here. So this is well, theta angle and the gauge coupling. So let me forget about the theta angle for the moment, and then it's just the gauge coupling. So the gauge coupling constant jumps here and by an element of phi. So this is like a Jones domain wall, and so there is something non-trivial here, and so there is some 3D theory which couples to this 4D n equal 2 series. I mean, there are a lot of gauge degrees of freedom here, and they couple to 3D series. And in general, if you can, after taking the duality, etc., you can show that you can decouple the 4D degrees of freedom. So you can regard this 3D n equals 2 series as its own theory. And in particular, you can consider half BPS domain wall such that the number of supersymmetry here is reduced from half as opposed to this here. So we have 3D n equals 2 theory. And so the proposal is that these two should correspond. In other words, let me say that again, that 3 manifold is now Riemann surface times interval, but with a twist by an action of the mapping class group. And then this corresponds to domain wall theory. Where the domain wall theory is specified by sigma times both of these. So first, sigma defines this for the n equals 2 SCFT. But it defines it because we can compactify the 60 theory on that. And we have a specific for the n equals 2 theory. And by adding this extra ingredient, we can construct the duality domain wall inside it. And then these are the 3D series. So this is 3D chern-simons. And then since this is another specific case where M takes a particular case. So when this M takes this particular case, this is the proposal. So I have a 3D chern-simon theory, so I can compute the quantity. And also this Tm is defined as this domain wall theory, and I can compute it. And it's a non-trivial task to compute both of these quantities and then try to see if it will match.
You didn't explain why is it 3D chern-simons here.
Oh, okay, yeah, right. So sorry, yeah, that's right. So it's so far it's just a 3D. Yeah, okay, so sure, I'm coming to that. So so far it's just a 3D theory. So I need to explain why it's a chern-simon theory, but anyway. So the question is, why is this? So probably I need to add here that this 3D theory is defined as the domain wall theory. And then another question is what the relation here is. And then the answer is that this 2D theory is the boundary theory of this chern-simon theory. So what does it mean? Well, so first of all, again we start from this AGT type correspondence. So what the AGT type story tells us that what kind of theory which lives on the Riemann surface. And so I said that there's a Riemann surface and times interval, but there's going to be a dubious theory. Which lives on the Riemann surface. And another question is whether we can lift this dubious theory to 1 dimension higher. And the answer is that this is going to be the chern-simon theory. SL to R chern-simon theory. Well, so let me explain why these things are related. And of course, the complete analysis requires careful analysis of the quantization of this chern-simon theory and careful analysis of the boundary condition, etc. But maybe probably the simplest way of explaining that is that the classically the dubious fields. So this dubious field, the origin of this dubious is actually from the complex structure deformation. On the Riemann surface. I mean, there's a uniformization story of this complex. But we are talking about basically the metric on this Riemann surface. And then there is a uniformization theory in mathematics which says that these complex structure metrics are conformal to the standard, say, sphere metrics up to a conformal factor. And then the condition that this conformal factor satisfies this, the complete metric satisfies this, the condition that the curvature is negative constant is exactly the same as the Review equation. That's how Review comes about. So the Review theory comes from this complex deformation, the metrics on the Riemann surface. And so in particular, it's described by the Zweibeins, since it's a metric on a two-dimensional manifold. And also we can add the spin connection. And we can regard these as independent degrees of freedom. But of course, then you have to put some constraints. That, like for example, I can be getting signs, some certain signs long. But, it doesn't work. there are some trivial equations for which defines this spin connection. So using this equation, I can eliminate these spin connections. But let's regard the spin connections as independent degrees of freedom, and then we can also write down the equation like E plus E minus equals to 0, where this says that curvature is constant negative. Because, well, actually, I forgot to say that I consider the case of the Riemann surface where the Euler character of this Riemann surface is negative. So it's going to be hyperbolic, 2D hyperbolic manifold. And then these equations can now be elegantly written in terms of E plus E. We can prepare a 2x2 matrix by E minus, omega, if I think I hope it's, well, the conventions can vary, but well, for example, I can define from these three ingredients, I can define a 2x2 matrix here, and then these three equations are now the equation that these f equal to 0, the gauge field strength for this gauge connection is 0. So, what I'm saying is that here is that so the review theory is about the complex structure deformation of the Riemann surface, and actually a particular mathematically the connected component, a particular connected component of the moduli space of the Riemann surface here is the same as the moduli space of flat connections, SL2R flat connections. And that's where we have this SL2R chern-simons theory comes about, because if you talk about the classical chern-simons theory, the only thing you have is that about flat connections, which is exactly the same as the one which appears here.
So basically, question. Naively, I would say SL2R chern-simons should give you SL2R with Zumina.
Exactly.
But are you saying it's precisely Liouville?
Well, actually,
are you saying it's equal to Liouville or what?
Well, let's see. So for that, yeah, actually both statements are completely correct. The same. I mean, so but the point is that we are choosing different boundary conditions. So the thing is that if you start on 3D chern-simons, SL2R chern-simons, and use one particular set of boundary conditions, you have SL2R with Zumina with more.
Yeah, that's what I don't see here. How I don't see your boundary conditions and how they differ from those which give you a SL2R.
Oh, let's see. So maybe I can try to go a little bit more detail about it. So let's see. Maybe I want to stay close to here. Okay. So anyway, I think people. So what I can do is so when we do the let's say quantization, well, probably we can start here. We can use it here for temporary. And what we can do is so we need to talk about the quantization of this chern-simons theory, for example. And then we have to choose the set of coordinates as opposed to momentum. That's the choice of polarization. And we have to choose that in any quantization. And then the degrees of freedom we have so let's see, well, people do first of all, canonical quantization. So you start on Riemann surface, regard this as time, and we're going to have a Hilbert space on this Riemann surface. And let me denote the coordinates of this Riemann surface by G and Z bar. And then we have the independent degrees of freedoms are A, Z, and A, Z bar. And A runs from 1 to 3, which is the dimension of SL2R. So these are the independent degrees of freedom. And so we have to choose 3 out of these. And the natural choice 1, which is standard in the literature, we just take this part, holomorphic part. So this is known as a holomorphic quantization. Yes, exactly. So, another choice is this choice, EZ plus EZ bar. Maybe minus, but anyway. I hope it's correct. But anyway. So I choose a different 3D. I mean, these omegas and E's are just the omegas here. So it looks like a little bit strange combination, but we can nevertheless do the quantization here. And of course, the wave function is going to depend on these 3 sets of parameters, for example. And but what we can do is that first of all we can write down the quantum version of the statement that it's a flat connection, namely this f applied to f as an operator applied to this wave function is equal to 0, and we write out everything in terms of these 3 components. And then what we can do is that first of all show that we can a little bit trivially solve with respect to this omega, but which is not surprising because originally these omegas are are not independent degrees of freedom because they are determined from E plus and E minus. And actually, this wave function has a Gaussian dependence with respect to omega. So they are not too important. And then there are two things remain, but of course there are gauge degrees of freedom. Namely, we can change the coordinates, and then there are still gauge degrees of freedom which acts on this E plus and E plus E bar. And so if you can write, say, the E plus is equal to E phi, or maybe I'm getting to dz bar, for example, E minus E phi dz bar plus mu bar dz. I hope people can see. This, you can write down. You can switch to other combination phi and mu, and depending on preference, you can choose. You can choose to retain either one of these, and this phi, for example, is going to be the UV field corresponding to that. So the statement, actually, the statement is subtle. Thank you for bringing this attention because this, as I said, this gauge chern-simons theory is a gauge theory. So you have to first of all. We quantize the theory using this epsilon E plus E minus omega as independent degrees of freedom, and then we have to impose some gauge symmetry. So the more correct statement is that the gauge independent part of the partition function on this manifold is captured by UV theory. Because as a boundary condition, there are some other things which are here, etc. But anyway, maybe things are becoming a little bit technical. So let me move on. But anyway. So simply put, the reason why this theory is related to this 2D review theory. Well, in this case, I'm talking about AGT. So we have review theory is the theory on the boundary of the chern-simons theory. So schematically written, the partition function so the partition function schematically written. If you look at this figure, it's easy to tell that partition function of this thing, Riemann surface times, it's moving, but never, it's going to be something like L phi hat, where these L's are the set of parameters which specify the boundary conditions. Actually, these L's are related to the complex structure deformation of Riemann surface, which is related to these stories here. But some details are not too important here. And then this partition function of the chern-simons theory can be written here in this form. Whereas, if you start from the partition function, let's see. So, well, you have some quantities here, and then the statement is that this is going to be the same. The statement I wrote here, which I deleted, sorry. It's actually remains. Just a half remains. So this partition function equals partition function. In this case, so this is going to be the right-hand side of partition function of chern-simons theory, and this is going to be the partition function of 3D domain wall theory. And it should have a set of parameters, which I write L and N prime. So what are these parameters? In other words, what are the parameter identifications? So the parameter identifications are the followers. And the parameter identification is the non-trivial part, because some geometrical information is now turned into the parameters inside the Lagrangian and vice versa. So let's see which part. Let's write 3D n equal 2 theory here. 3D chern-simons, SL to R chern-simons theory here. And first of all, but I forgot to say one thing. So when I say this, we can define but the chern-simons theory. One obvious question is that chern-simons theory has one parameter, which is the level. So what's the counterpart of that in this part, in this story? And it's going to be the B splashing parameter, where you are deforming S3 to be S3B, which is defined by Z1 squared B inverse Z2 squared equals to 1. So this is the definition of S3B, and there's a one parameter for that. And actually, you can do the localization computation for S3B as well. And this is the same parameter B, which appeared in the introductory part of my talk, but maybe people don't remember. But anyway, there is the parameter, one parameter deformation on this side as well. So this is geometrical. This is the parameter of the Lagrangian, which is why it's non-trivial. And then there are a set of parameters, L and L prime, which are the boundary conditions. Boundary conditions. And this corresponds to mass parameters or Fi parameters. Of the 3D n equals 2 series. I didn't, well, it seems that I don't have the time to talk about explicit matter contents, etc. But these are the specific 3D series, so it's easy to imagine that there are mass and Fi parameters for these series. So well, I use the same notation, n and n prime. And then also I was talking about this phi, which is the most, well, let's see, first of all, this sigma. Sigma defines for the n equals 2 series. And, well, there's the same sigma here, which is in the part of the definition, the same sigma which appears there. And also there's phi, the element of the mapping class group. And together with these, I can these informations, I can construct 3 manifolds with boundary conditions. Remember that these element primes are the boundary condition which we place there. And here on this side, as I note, this phi is an element of S duality group. And combining these ingredients, we define a 3D n equals 2 series as a domain wall series. So for example, these data are geometrical. They are the data defining the series, etc. So but these are the parameter identifications. And then there are several things, several concrete systems. Well, so far, I just talked about some general line of arguments. But what I'm saying is actually can be derived from AGT in together with a little bit of assumptions. In particular, the 2D Liouville theory mathematically can be formulated as a so-called Teichmüller theory, the theory of complexity deformation on the Riemann surface, which is a little bit sometimes useful because it's formulated mathematically. And using that formalism, I can give a general argument why the equivalence of partition functions are the same. And well, in the remaining 5 minutes, I'm going to tell you.
How do you go from S4 to S3?
Oh, actually, well, in this story,
If you derive it from there.
Yeah, that's right. That's right. That's the story of Davide, Jaume, and Nadaf. And so, okay. So I didn't explain that part probably, but in the remaining minute, let me explain that. So maybe the connection of these two AGT is not completely clear. Maybe. So let me explain again. So a little bit with a slightly different viewpoint. So well, in AGT, we start from the partition function for the n equals 2 series on S4. Okay, and then. Well, very schematically, I would like this is the integral of the square root of z negros of and z negros of r. I mean, this inner product means the integrate of the Coulomb branch parameters. And then this is going to be related to the conformal blocks. But again, the correlation function in the Liouville theory, the vertex operators in the Liouville theory, and it factorizes it into the product of conformal blocks. And we integrate over, maybe some people would like to see the parameters. So we are going to integrate over Coulomb branch parameters. And these are integrating over internal momentum, Liouville momentum. So this was the story of AGT. Basically, there are north pole contributions, south pole contributions if you do the localization. And we can talk about a certain generalization where there is no color. Okay, so let me try to use the wavy line here. We can put some non-trivial domain wall theory, duality wall here. So it's we are changing the theory. Another way of saying that the complex structure, I was explaining this duality wall in terms of flat space and there is flat, but yeah, that's right. Because I mean, if you do the localization, everything is not. You only need the local information, so you can do this. And then it's natural to guess that the structure should be Z3D, where Z3D is the partition function of this 3D theory. And well, maybe I can write them more chemical parameters. There are some parameters, A and A primes. Where these A and A primes are actually the same as L and L primes, which appear there. So they are going to be mass and Fi parameters. And the reason these parameters appear is that these mass and Fi parameters are defined as a particular component of the vector superfield. In other words, if you have gauge symmetry in the 3D theory, and you can try to weakly gauge it by degrading the background, by introducing background vector superfield coupling to that global symmetry. And then we can gauge it. And then if you gauge it, then these mass and parameters, Fi parameters, are now promoted to dynamical fields, which are the scalars and the scalars of vector multiplet. And then these are the parameters. And similarly, we can talk about the natural question: what are the counterpart of that? And schematically, it's going to be the action of the mapping class group here. In other words, you can try to put on similar indices here. And the meaning of this F hat is that it represents the action of the conformal block, mapping class group on the conformal block. For the mean, probably I'm going to write down the notation. But there are external momentum, internal momentum, which is the same as here. And then there is a complex structure. So this is a conformal block. But you can change this to phi of tau. And then try to see what kind of quantities we have here on this side. And then there are some major factors coming here, but this is going to be represented by a matrix, infinite dimensional matrix. So this is the same as this one. And if you compare this ingredient, it's natural to guess that conjecture that these two ingredients are the same. And this is what conjectured by Luca, Gaiotto, and Gomez. And so by comparing this, it's natural to see that this 3D partition function on S3 is the same as this one. And then this structure is, you have to change the basis actually, but this structure is very similar to the structure which you have here.
But there you was thinking in terms of 3D manifold. I thought there you think of L as a state in Liouville and phi hat acting on that. No, maybe.
Oh well, let's see. So this itself is a 3D theory, but we are doing the canonical quantization. So the states are defined on the Hilbert space, which is the size where constant time size of the 3 manifold.
Yeah. Does L correspond to a state in a Liouville theory or not?
Yes, it corresponds to stating.
So phi hat I can think of acting as a state, as an operator acting on Liouville state?
Yes.
But it's not quite the same. Or are you saying it's the same statement as
yes, so actually, so the state.
Is it the same?
Yeah, so there is a Hilbert space of conformal blocks, and one non-trivial, highly non-trivial, very non-trivial statement is that these L's, which I wrote schematically, are the complete set in the Hilbert space of conformal blocks. That's a non-trivial statement. Sure. Yes. More concrete statement is that these have, so forget about external momentum, there are 2 parameters, alpha and tau. And this conformal block can be written as alpha inner product and 2 states, alpha and tau. But this was, I wrote L, sorry for the notation, but they are the same. And so there are 2 different bases, but each of them spans a complete set. And actually this state L is a very good state, which is orthogonal to each other with respect to certain measure.
So L is essentially Liouville momentum?
Yes, Liouville momentum, yes.
So what's the definition of the Hilbert space? R?
Let's say, the Hilbert space on this Liouville side.
Yeah.
So it's going to be the Hilbert space of conformal blocks. Or if you like a more geometrical formulation, it's a Hilbert space coming from the quantum Teichmüller theory. In other words, Teichmüller theory is a manifold with symplectic manifold. So it has a symplectic form. So you can do the standard canonical quantizations and then obtain a certain Hilbert space. And so there is a conjecture that the Teichmüller Hilbert space is the same as the Liouville Hilbert space. So if you believe in that, you can use both formulations.
Usually, it's into within your model. Usually you have the Hilbert space of conformal block within your model, which is finite dimension.
Okay.
So how about in this case?
Oh, okay. So in this case, probably actually, thank you for bringing that. So it's an infinite dimensional Hilbert space, and it's the same in both in supersymmetric side and non-supersymmetric side. So on the supersymmetric side, I was talking about this partition function Z3D, and I didn't have time to write down the explicit expression, etc. But it's written as an integral. Integral because if you do the saddle point analysis here, there is an integral over the scalars and the vector multiplet. Here are the sort of continuous saddle points you have to integrate. And that corresponds to the integral here in this Liouville. Liouville momentum is continuous here, so there is an integral as well. And also that's the same in chern-simons theory as well. Because the difference is you need to keep in mind that we have SL to R chern-simons theory. So which is the analytic continuation of the usual SL2. And if you talk about the representation theory of SL to R, for example, there are infinite dimensional representations spanned by a continuous parameter. And this L state L is such a state, such a continuous state.
Okay, and then one more question. So you use SL2R, right?
Yes.
And then you just mix SL2R and SL2C, and then you just take only holomorphic part?
But I'll say that in this story, it's just SL to R. I think it's because, for example, one thing I was explaining around here is that the modular space of trichimeral space, well, the modular space of complex structure deformation of the Riemann surface is the same as flat P SL to R flat connection. That's the mathematical statement. And also there is a corresponding DL slice which is chosen in here, for example. In the matrix model computation, for example, there is an integral, but we are integrating with a real number. Because we are integrating with scalars and vector multiplet, which is a real number. So I think we are definitely choosing the real strides. But if we want to go to SL2C, probably, well, first of all, we can talk about analytic continuation. And for some of the quantities, SL2, it doesn't really matter if whether we have SL2R or SL2C. Because one maybe quick explanation is that if you have SL2C chern-simons theory, the Lagrangian splits into the homomorphic part plus an anti-homomorphic part. So unless you talk about some instanton contribution, etc., but and if you focus on the expansion around the classical flat connection, then these answers don't match. And also, if you want to, well, we can start from 3D n equal 2 theory and dimensionally reduce to 2D 2, 2 series, for example. And then the scalars in the vector model will get complexified, so we have something complex. And I think that, and then in that context, it's more natural to start with the SL to C flat connections.
You mean M is S1 plus R2 or something?
Okay. So yeah, I'm talking about compactation on the supersymmetric compactation S3.
Oh, I see.
Yeah. Okay. So let me actually. That itself is an interesting story. So let me explain why I'm completing stuff where to write. Let's see. Maybe I use here. Yes. So. Oh, maybe okay. So. Oh, okay. But let me spend 3 minutes for that. So you have a 3D partition function on S3, S3B, where S3B was defined somewhere there, here. And then take the limit where B goes to 0. And you can show that S3B becomes R2 times small S1, where the size of this S1 becomes very, very small. So by formally taking this limit, we have 2D 2, 0 theory, sorry, 2, 2 theory on R2. And then, actually, if you talk about the parameter indications, these B and K's are inversely proportional to each other. So B goes to 0 corresponds to K goes to infinity. So this is chern-simons partition function on M. But it goes to the semi-classical limit where K goes to infinity. And it's natural to imagine that the semi-classical leading contribution is the chern-simons invariant of the 3-manifold. Well, because chern-simons invariant is just an integral of the chern-simons form on the 3-manifold. And if you talk about, as I was saying, here in this context, it's natural to complexifize things. And we have the volume of the 3-manifold. And then for hyperbolic manifold, these are the crucial, very interesting invariants mathematically. They are very concrete numbers, which have a lot of meanings in number theory, for example. And there are different ways to compute it. And we explicitly start from here and then show that it produces the correct hyperbolic volume of the 3-manifold, which is another check of this equality. And also, maybe I should mention that there is also connection with integral models, because in this recent story about necrosol stability, if you have 2D 2, 0 theory, there is a quantum integral models corresponding to that. And so there will be the deformation XXZ models and their deformations. And so So I'm trying to work on it in that first part 3, and so there are also interesting connections to integral models. And finally, I was talking about the case where the 3 manifold is just a Riemann surface times an interval, and I didn't talk about the complete general case. But actually, if you want to obtain more general 3 manifold, there is an operation that in this Riemann surface times interval has a boundary, but there is an operation of attaching something to the boundary called a handle body. And that, if you can do that, you can actually generate any 3 manifold. So there should be an operation of J-theory operation of closing off the boundary, incorporating the handle bodies. And I think it's an interesting problem, and partly did that in the Taichi theory. And but anyway, but it's still work in progress. Okay, thank you. Maybe I should finish. Let me finish here. Thank you.
Do you know what is the theory for the handle body?
Sorry?
Do you know what is the theory?
Oh, for the handle body. The answer is no, unfortunately. But there are certain speculations. For example, one speculation I made first is that, for example, please look at this structure which comes from 4D gauge theory. So it has 3D something, and it's somewhat reminiscent of this of the Hegel splitting story. In other words, there is something called a handle body here. There's an action, something corresponds to the action of mapping class group in the middle, and records. So natural speculation I have at the time is that maybe this Necros partition function is somehow connected to this handle bodies in the chern-simons theory. But it's a pure wild speculation. And I have a more technical way of using handle. Instead of saying that we have a handle bodies, we attach handle bodies, we can say that so let's see. So if you start from Riemann surface times interval, for example, there are boundary Riemann surface, and then there are triangulation of that. But then there's operation of crushing the boundary of the Riemann surface and by closing off. Instead of saying that we are touching something, we can crush. We can group the faces of the Riemann surface. And then that operation can be realized in the Taichi theory, or more in the like a Liouville theory. So I have come to started from chern-simons theory and come to Liouville theory, but haven't figured out the meaning of gauge theory yet.
Which operation is how is that?
Well, it's actually just setting one of these Liouville momentum to a very particular value. It's a special value.
What's the complex
Well, actually, the more correct statement is the forest. So these are the parameters, but we can go to a different basis. And then let me call that parameter x, for example. So these are going to be the Fock coordinates in Taichi theory, for example. And then the operation which I was referring to, that let me set one of the parameters x to be pi over 2 or something. And if you want to use this language, there is a non-trivial, highly non-trivial transformation of variables between this and that. But it should be the transformation is already known, so we just have to plug in and try to see what the meaning of that, etc. Well, pi over 2, roughly speaking, is like you have a 3 manifold, and the 3 manifold can be grouped from tetrahedron, so there are dihedral angles between faces. And we say that, for example, the faces coincide, which is like the sum of the angles summing up to pi or something. Right? So it just says that some of the faces of the tetrahedron coincide. And that's the condition that these parameters are pi over 2. And I wanted to see the meaning of it in this language. And that would be interesting. And if it's going to be related to this Necros, that would be much more interesting. But there could be some more modest interpretations in gauge theory. Okay.